So welcome everybody. Thank you very much for joining the NanoStream project webinar this afternoon. My name is Claire Scantleberry from the Nanotechnology Industries Association, and I will be moderating this session and just looking after the slides and attendees. In terms of the running order for today, we have a number of presentations with 2 Q&A sessions halfway through and at the end, and all members on the webinar are very welcome to ask questions either directly verbally or using the chat function in the control panel of your GoToMeeting software. So we will keep everybody on mute if that's okay. We are also recording the session so that we can put it on YouTube afterwards and you can all become internet sensations for the right reasons. But we have a super busy agenda today, so I'm going to immediately hand over to Dimiter Prodanov of IMEC to introduce the project and the webinar today. So please take it away, Dimiter.
First of all, thank you very much for organizing this for us, Claire. This is very nice. Could you start with the presentation? Okay. There are 2 approaches to nanotechnology, a top-down nanotechnology and a bottom-up nanotechnology. The bottom-up approach can be traced back, the understanding can be traced back to the famous lecture of Feynman about the space in the bottom of the world. And in this type of nanotechnology, the main building blocks are the engineered nanoparticles, and there are various functionalizations and interactions. However, this seminar is about a different type of nanotechnology, notably nano electronics, where we have the top-down nanotechnology in the sense that macro objects are functionalized by growing nanomaterial coatings, or engineered nanomaterials are embedded in a solid-state matrix. So a prominent example of this is nanoelectronics. Could you go to the next slide, please? Where we have a number of occupational health and safety challenges in the innovation chain, because the action of the Moore's law, which you see here on the bottom, mandates use of novel materials and novel architectures in order to decrease the feature size. So that results in a constant innovation process with increasing complexity, and we have more than 200 chemical products that are used in the current manufacturing of chips, and almost all chemical elements are tried on. Here in the center you see actually a list coming from IMEC, where I work, about different types of compounds that we use in different experimental processes. So that brings us to the necessity to map the use and to project the future exploitation of different technologies. Could you go to the next slide, please? Now, why do we focus on nanoelectronics in terms of nano safety? That's the first thing that I said on the last slide was about different challenges. But secondly, on the bright side, the nanoelectronics is a key enabler of industrial development. Here are different examples, such as radios, MEMS sensors, LCD displays, different GPUs and CPUs. And to map the progress of this, we can think of the Apollo 11 system, which could be run in principle on an iPhone today or Samsung Galaxy. So this process has very stringent environmental health and safety practices put in place in order to enable this constant type of and process of innovation. So we can think that the health and safety policies which are related to the use of engineered nanomaterials can be safely implemented in nanoelectronics, and it can serve as an example for this process. Could we go to the next slide, please? That brings us to the composition of the NanoStream consortium, which includes 14 partners from 6 different European countries. We have representatives having strong material R&D processes, such as IMEC as coordinating institution, Fraunhofer IISB, Tyndall, but we also have a lot of semiconductor industrial participants. For example, coming from Intel, from NXP, from ST Microelectronics, Texas Instruments, Soitec, and L-Foundry. We also have some specialists in health and safety assessments, such as TNO from the Netherlands and Premed from Belgium, and also some nanomaterial and environmental specialists in monitoring and measuring practices, such as CEOA from France, Vito from Belgium, UCD from Ireland. So this is the composition of the NanoStream consortium. And could you go to the next slide, please? In the beginning of the project, we have set up several ambitious goals to bring forward better understanding of the occupational hazards which are related to the use of nanomaterials, also to provide and enable better governance for the risks that are related to the manipulation of such materials in the environment and at the working floor. Using our industry as an example, and also to intensify the international cooperation both within and outside of the consortium, and to promote the public knowledge in the understanding of the occupational hazards which are related to the nanomaterial use in the semiconductor industry. So these are our ambitious goals. Could we go to the next slide, please? What you see here is a picture of the kickoff meeting of NanoStream, which happened on the 28th of January 2016, where we also clarified the objectives, and we had pretty detailed objectives to build inventories of materials and research topics and directions which are relevant for the current and future use of nanomaterials, but also to identify gaps in the knowledge and also gaps in the methodologies to assess the risks of these nanomaterials. We also looked into how this can be used by the industry in the assessment of both purchased and incidentally released products of manufacturing processes. And we also wanted to use the results to enable better governance and to provide outreach and dissemination both inside and outside of the consortium. Could you go to the next slide, please? For that purpose, we proposed a comprehensive approach to the safety of nanomaterials, where we looked at all the relevant aspects, such as the material properties, the health effects, if they are known, the release characteristics, again, if they are known, what will happen in the environment, and what will happen at the work floor in terms of occupational exposure, in order to provide a comprehensive risk assessment. While in the risk mitigation approach, we also looked into how the risk can be measured or quantified or categorized, what kind of engineering controls are necessary or prescribed in certain circumstances, good work practices, and also, most importantly, how we can train the workforce in order to understand the risks and how to communicate with society in order to properly convey the risk along different parts of the supply chain. Could we have the next slide, please? So our project methodology was pretty straightforward and linear in terms that we started by mapping a prioritization of materials and activities. Then we looked into the hazard to identify the hazardous characteristics of the materials, and we also looked at the exposure assessment. So there we started looking into different processes. We also looked into the medical supervision practices. And in the end, we also looked how this information can be made available in terms of training and dissemination materials. So you can find a lot of information on our project website, which is given here. It's nanostream.eu, and it will run until, I think, 2020-21. So no matter that the project ends in a couple of weeks from now, on the 31st of December, the information will still be available for a number of years. Okay, could we go to the next slide, please? So in part one of the seminar, the next speaker will be Fiona Moclair, who will explain how engineered nanomaterials are used in semiconductor processing. And then we have three related questions on how can we perform risk assessment of the purchased nanomaterials, which are the main gaps that are related to the generated nanomaterials or process-generated nanomaterials, and also how can we measure emissions. And the speakers will be Lieve Geerts from Vito and Maaike Le Feber from TNO. And then next slide, please. Then we will have a short Q&A session, as Claire explained. And in the second part, we will discuss the development of competences and training. That will be Daniela Iacopino from Tyndall. We will also have some remarks about the communication of the risk along the supply chain coming from Peter Belde from NXP. And we will also talk about future materials and the presented risk assessment framework. And that will be a talk from Michael Jank from Fraunhofer. And then we will end up with a round table of the industrial participants from the consortium. And we will have a second Q&A session. Okay. So with that, I would like to open. Yeah, I'm done here. So we can move to the next speaker.
We certainly can. Thanks very much indeed for that introduction, Dimiter. I am now going to hand over to Fiona, who can introduce herself and present her slides from the project. Okay, Fiona, take it away.
Thank you very much indeed. Yeah, thanking you. So Fiona Moclair is my name, and I'm a senior environmental engineer in Intel's corporate EHS organization. And as I say, my role in this particular consortium was that I was what we call the Work Package 1 lead. And today I'm going to give you, I'll call it an introduction really, in terms of how engineered nanomaterials are used in semiconductor processing. So from here on in, I'm just going to call them nanomaterials, but we are looking at engineered nanomaterials. So Claire, if you want to take me to the next slide, please. Okay. So, you know, the world we live in today, without a shadow of a doubt, products that contain semiconductor devices, or some of you might not know them as chips, they are all around us. You know, going from cars to smartphones to tablets, even the smart home, you know, where a lot of functions are now been automated, to medical scanning equipment, even to the likes of devices that monitor your own activity and your fitness, to the traditional workhorses nowadays, you know, be it your laptop or indeed your regular IT equipment, be it a PC. And to be honest, you know, these products just simply would not exist without what we do as companies. And there's just an example of some of the semiconductor devices that we'd actually utilize. So Claire, if you want to go on to the next slide, please. Okay. So again, I don't know what level of knowledge folks have on the webinar itself, but at its entry level, semiconductor devices basically are derived from, of all substances, sand. Then it moves on to what we call a silicon wafer, and then you get the device that people are pretty familiar with today. But with this technology, this just would not happen without the use of engineered nanomaterials in the manufacturing process. Just simply wouldn't happen, and that just shows how critical these nanomaterials are to our entire industry. Claire, next slide, please. Okay. So in terms of, the fabrication of these devices, or indeed chips, it consists of literally hundreds of precisely controlled steps, which in turn result in a series of very much patterned layers. And this consists of a variety of different materials, all one on top of another. When I look at a silicon wafer now, we would have you talk about in excess of about 30 different layers that would build up that chip for you. So it is a very complex process. And this activity, it's actually undertaken in what we call a clean room. This is an extremely clean work environment. And I think most of us on the webinar today will have been unfortunate enough to have to go into a hospital operating theater at some point in our lives. But to think that a high volume manufacturing clean room will be about 10,000 times cleaner than your typical hospital theater, that just puts it into perspective in terms of the work environment in which these devices are actually made. So Claire, next slide, please. Okay, so the next number of slides contains what I would call a high-level overview of the manufacturing process. And really the intention of this is just to give you, I'll call it a 101 level introduction, but it's also to show you what part of the process that we actually utilize these engineered nanomaterials. So again, I'm not going to go into an awful lot of detail, but at a high level, one of the first things that we absolutely utilize is that, we take that silicon wafer and we apply what's known as a photoresist. Now that has a tremendous function for us, and in building up the different layers, photoresist is basically applied, it's exposed and washed off at different instances throughout the process. That's undertaken simply because we want to implant what we call ions. So again, I'm sure quite a lot of you are very familiar with this, and at the end of the day, we're talking about positive and negative ions. And this, at the end of the day, then, as I say, it does manipulate the wafer's conductive properties. And then after that, we do look at the removal of this photoresist, because once that's done, you do leave behind the conductive properties that are basically engineered onto that particular wafer. So Claire, next slide, please. Now, the next section in terms of this wafer, what happens to it goes into what is known as photolithography, or litho is the common terminology we use. And this just goes into a little bit more detail in terms of what happens here. So basically, this wafer will be actually spun while the photoresist is actually applied to the wafer itself. And this allows for a very even application, which is terribly, terribly important. Then the next thing is that we want to expose this photoresist to ultraviolet light. And one of the effects of this is that it basically makes the photoresist soluble, and also it allows us then to basically generate very, very distinct circuit patterns on each of these layers. And I said earlier, you can have about 30 different layers on any of these wafers. Now, as I say, there are loads and loads of different processes involved, but we're just going to focus now on the transistor. I think most people will be familiar with transistors. So with that, Claire, if you go on to the next slide, please. Okay. So the next step in the process is an area called etch. And, the first portion of this is that we're looking to wash off that photoresist. And ultimately, this will reveal the distinct pattern that is needed, and this is done by a mask. This whole area will be called mask operations from that perspective. Then in etch proper, what we're looking at here then is that the photoresist itself will protect what we call a high dielectric constant, and this is what we want to hold on to. We don't want this to be etched away. So again, this is one of the functions of that photoresist. And then the revealed material will be etched away with the necessary chemicals after that. And when all that process is undertaken, we then, as I say, remove that photoresist. Okay, it served its function. We then get rid of it. Next slide, please, Claire. So now we're into metal deposition, and you know, at this stage now, what we call the transistor is almost ready. And what we do at this stage then is that, you know, any of the holes that have been etched, they'll need to be filled with the likes of copper or any other material in order to make the various connections that we need within the transistor itself. After that, we introduce some electroplating, which again, I think most people will be pretty familiar with. And at the end of the day, what we have is that copper ions then will be deposited on the transistor itself. And then you have, as I say, after that, you've got the post-electroplating stage. And this is where we have the ions themselves, these copper ions, they settle as a thin layer of copper on that wafer surface. Now, Claire, if you go on to the next slide, please, for me. Okay. Now, there's two distinct steps I want to talk to in the metal layers, but you'll see one of them is highlighted with a little circle around it. And really, this is just to illustrate for some of the semiconductor manufacturers, this is one step where they will utilize, as I say, they will actually utilize nanomaterials. And this is in an area called polishing. And you'll see when we get into a few slides later down the slide deck here, that this is the most critical area within semiconductor manufacturing that utilizes nanomaterials. So we will talk in a lot more detail in a few minutes on that one. And then, as I say, you have metal layers. So there's a variety of different metal layers then are actually built upon in order to create these very, very important interconnects. And as I say, these devices can have in excess of 30 layers. So Claire, next slide, please. Okay, so now we're coming towards the end of the life of a wafer, as you call it, because you know, after these wafers are tested in what we call sort, effectively at that point, the wafer itself, it's cut up into the individual die. So these are the individual pieces that ultimately become the semiconductor device that you're familiar with. And at that stage, you know, we hold on to the die that pass all the functional testing, and at that stage, the ones that do pass it, we basically process them further in different facilities in order to package them, and it becomes the product that you'd be pretty familiar with. So as I say, that area of polishing is one of the key areas when it comes to our use of nanomaterials. So Claire, if you move on to the next slide, please. Okay, so in terms of this, you'll have heard me talk about the likes of photo in terms of photolithography and the resist that we use there. We do have some of the companies in the consortium that utilize a colored resist, but the biggest use of our nanomaterials is in what we call slurries within this polishing area. And simply because of the little chart there, in terms of the nanomaterial usage, you'll see that 98% of our nanomaterials that we use are in a slurry form, but used in this polishing area. And the official name for this area is known as chemical mechanical polishing, or CMP, the term that we utilize quite a lot. So from here on in, I'm really going to focus on CMP because it is by far the part of the process that we will be looking at. So Claire, if you go on to the next slide, please. Okay. So in terms of these CMP slurries, so the slurries themselves, right, they contain what we class as abrasive grains, and you can have the likes of cerium dioxide, silicon dioxide, and also aluminium dioxide, and these are all in nano, right? The slurries themselves, they're odorless, tend to be milky looking. If you didn't know anything else, you'd think it was a bit of milk you were looking at. And as I say, they are stable suspensions, as I say, that are indeed dispersed in water. So as I say, they are, as I say, a fluid in that respect. But ultimately, they also, as I say, contain rust inhibitors, and also, as I say, they also tend to be alkaline in nature. And the image that I have there is just to show you the inner chamber of a CMP tool, whereby that round plate there, that's basically where your wafer will go onto. And that white arm that's basically hovering over that round plate, that's where the actual slurry will be displaced from. So that will basically, so now you've got your ingredients right in terms of this abrasive slurry, and that silver object under, overhead, that then will be lowered on top of that wafer, and then it literally polishes it away in terms of it gets rid of any unknown substances and so on like that, but greatly enhances the qualities of the final product. So Claire, next slide, please. Okay, so again, the function of this polishing really is to get rid of any of the unwanted conductive or dielectric materials on the wafer itself, right? And the spin-off effect of this really is that the semiconductor manufacturers can shrink their devices by making the wafer surfaces flat, smooth, and flawless. And also, as I say, it allows us to lay down a fine wire in terms of the patterns that are needed for this. And really the function is a quality function within the manufacturing process. Because ultimately, if we didn't do this polishing activity with the use of nanomaterials, you know, the device itself could have the likes of shorts and opens, which ultimately would result in the failure of that device to operate properly. So absolutely necessary in terms of the performance of that semiconductor device. Next slide, Claire, please. Now, with respect to ourselves in the NanoStream consortium, believe it or not, right, there were 16 different tasks identified with the CMP process. And these 16 different tasks were basically identified across normal operations, your preventative or your corrective maintenance tasks, and also any accidental operating modes. So quite a number of tasks around this particular tool. Again, we just have an example of a full CMP tool there onto the right-hand side. And in terms of, you know, what did we actually find when we actually did our analysis of this? Well, basically, we found that about half of all those tasks, so you're talking about 8 tasks or so, had low amounts of nanomaterials, nanoparticles available for exposure. And those that did have availability for exposure did have a low potential for dust or aerosol formation. So again, we're looking at how a worker could inhale these particular nanomaterials. So ultimately, you know, from a worker exposure perspective, what we're seeing here is that through, you know, the risk assessments that were conducted, were found to basically be of a low concern from that perspective. So Claire, if you go on to the next slide, please. Right. So to sum up then, you know, in terms of life today in the 21st century, semiconductor devices are an integral part of how we live. Those devices, we cannot manufacture them without the use of engineered nanomaterials. Simple as that. Now, as I say, we have the likes of these materials used in photolithography and indeed CMP. CMP being the one where we utilize these the most. As I say, 98% of these nanomaterials are used in CMP. And without the CMP slurries, you know, this will lead to quality issues with the devices, something we just don't want. And ultimately, from NanoStream's research, you know, the potential for worker exposure across all those different 16 tasks, we found this to be basically low, which again is good news from that perspective. So folks, that's me done, and I'll hand you back to Claire.
Thanks very much indeed, Fiona, for a fascinating insight there. And we are going to jump straight to our next presenter, who we have 2 presenters, Maaike and Leva, and I'm going to transfer the screen over to Maaike. And so, Maaike, you can introduce yourself and say hello while the technical wizardry is happening. And hopefully everybody will see Maaike's screen in a couple of moments. There we go. Thanks, Maaike. What we can't do is actually hear you, Maaike. Are you still on mute?
Yeah.
Yeah.
But I wasn't, and hopefully you now also see my screen.
Yeah, we can see your screen and we can hear you very well. So please take it away, Maaike.
Do you also see the GoToMeeting?
No, we just see your slides.
Okay, very good, because then I can still arrange things with you. Okay, my name is Maaike Le Feber. I'm from TNO, and we are quite heavily involved in risk assessment technologies, approaches for nanomaterials. So that's exactly what my presentation will be about. So this is not working. Actually, I will tell you a bit about how to perform occupational risk assessment, what are available tools around. Based on that, what NanoStream approach did we choose and what were our experience with that. Is it possible to measure exposure in clean rooms? And I'll end with some thoughts on combination of measurement data and quantitative models together. And as a last part, I will tell you the main gaps we encountered. So how to perform an occupational risk assessment. To present that to you in a nutshell, you calculate the risk index, and you can do that by comparing an exposure concentration to a threshold value. So some of you maybe know this risk index as a risk characterization ratio, as it's called in REACH. So if the risk index is below 1, the risk is controlled. If the risk index is above 1, the risk is not controlled and you need to take action. But of course, this leads to the questions, how to assess exposure concentration and which threshold value do you use? To inform you a bit about this, we have to take a look at the risk assessment framework that we've once published. In this kind of tree, you see 2 branches. One is on hazard assessment, one is on exposure assessment. The hazard assessment, of course, is related to the threshold value, and exposure assessment to the exposure concentration, which we both need for the risk index. This framework is developed from a risk assessment perspective. So it starts with the very best option, and the very best option is, of course, to collect toxicity data for the nanomaterial that you want to assess and measure the exposure to the same nanomaterial in the scenario that you would like to assess. This is exactly why on top there is a box characterization. This characterization should verify that you do the hazard assessment and the exposure assessment for the same material. We all know that this is an expensive way of doing your risk assessment. So if you cannot do it on this level, you could use comparable substances and comparable scenarios and see what measurement data you can use from that to do an approximate assessment for your situation. And then we have even a lower level where you use quantitative models and you use quantitative reference values for the threshold value. All these 3 levels lead to quantitative risk assessment. Then, if none of these are possible, you can always do a qualitative risk assessment where you combine a hazard band for your nanomaterial with an exposure band for the scenario that you want to assess. And together they will give you some kind of ranking prioritization of scenarios towards the others. It gives you information, it's not a real risk assessment. To find out how we could use this for NanoStream, we did an inventory of available tools that do something with nano risk assessment. So we found quite a lot for hazard assessment, differing in dossiers with toxicity data, databases with toxicity data, reference values, and also approaches how to derive occupational exposure limits from these toxicity data. On the other hand, we also found for exposure assessment different tools that were available. Of course, prescriptions how to do measurements. We found databases with measurement data, and also a couple of quantitative exposure models. But most of the tools that we found were control banding or risk banding tools. Now, having seen this, we also know that in practice, people hardly ever start with the best method to do risk assessment. In most cases, we start with a control banding or risk banding approach. And if we can show that it's apparently safe, then we don't continue. But if we cannot demonstrate that it's safe, we will refine our assessment. So in practice, we will go through this framework from the bottom up. And that is exactly what we did in the tiered approach that we developed for NanoStream. So again, on this slide, you see an exposure assessment branch and a hazard assessment branch. The tier 1 starts with a qualitative banding approach to prioritize scenarios. And this is exactly what the industry partners have done in the NanoStream project. They have prioritized the scenarios for quantitative assessment using this banding methodology. So in the second tier, we selected the quantitative tools that were available, the state-of-the-art quantitative modeling tools, and we proposed them for different source domains. So under the exposure assessment line, you see 4 different source domains, and these domains are characterized by the appearance of the nanomaterial that you're exposed to. So for manufacturing processes, it's mainly the pristine particle that you're exposed to, while for nanomaterials in a solid matrix, it's the nanodust formed by abrasive activities. So it's solid aerosol that may or may not contain nanomaterial. For the nanomaterial in a liquid, it's a dispersion. So you will be exposed to a liquid aerosol, small droplets, with each droplet may or may not contain the nanomaterial. And for the nanopowder, you will also be exposed to pristine particles, but probably these pristine particles have a much higher agglomeration and aggregation rate than for the manufacturing processes. So these source domains are characterized by the appearance of the nanomaterial that you're exposed to. And what we found is that different tools, quantitative tools, are best suitable to assess exposure to different appearances. So in tier 2, you see that the NanoSaver is proposed for manufacturing processes and nanopowders, while ART is proposed for abrasive activities, also can be used for nanopowders, and Consexpo is proposed for nanodispersions. On the hazard side, well, we found out, like most of you probably, that not many nano occupational exposure limits were around. So we proposed there to use the bulk material OAL or the nano reference value, the one that is the lowest of the two, to be on the safe side. And in the tier 3, just like in other tiered systems, we go to the measured data and generated toxicity data. So what we try to do with this framework is we skip to tier 1 because the industries use tier 1 to select scenarios that could be tested by the tools proposed for the tier 2. So we've been testing the tools, how applicable are they to be used to assess the nano risks for the prioritized scenarios. And these are the experiences that we gained. I try to summarize this. Again, it's Consexpo, NanoSaver, and ART. Consexpo for liquid dispersions, as I just told you, NanoSaver for nanopowder, and ART for abrasive activities. But if we go deeper into the tools, we know that Consexpo actually is developed for consumer scenarios. NanoSaver is for occupational scenarios, and also ART is for occupational scenarios. Consexpo is developed as a nano-specific tool. NanoSaver is also nano-specific, but ART is not. So then we tried out to describe the scenarios, and we found out that it's quite hard to describe clean room conditions with Consexpo. not very surprisingly, because clean room conditions is obviously very far from scenarios that consumers normally encounter. But also NanoSaver was difficult to describe the clean room conditions, whereas in ART it was possible to describe the clean room conditions. So for the applicability, in the end, we noticed that none of the scenarios that were prioritized were about spraying, so about a liquid aerosol formation. So Consexpo turned out not to be that applicable. For NanoSaver, the near field estimations could be used, but to gain these estimations, the tool required input data that were quite hard to obtain. And besides that, we found out that the tool is a bit of a black box, so it gives you an answer, but you don't know exactly how it's been generated. Then ART gives you task-based exposures, and it's combined with a report in which you exactly can see what your input was to gain this exposure estimate. All tools are web-based and freely accessible, but NanoSaver had just a new version on the web and it had some bugs, so we had some trouble in testing it. And the conclusions were that Consexpo maybe is applicable for accidental scenarios where liquid aerosols are formed, but outside in clean room. We didn't test it. We have a feeling that maybe it is applicable to that. Whereas NanoSaver is a tool that provides wristbands with control advice, which is very much appreciated, but it requires detailed input data and is not very transparent. And ART, the tool provides task-based personal exposure estimates, but ART is not validated for nanomaterials. So actually what we found out is that each of these quantitative models, even though they are the state-of-the-art quantitative models, are not that applicable to the scenarios that we wanted to assess. So then the tier 3 is performing measurements. Within the project, the measurement devices have been screened, and also the standards for how to measure exposure. And we found out that there are methodologies available, and they are mainly based on tiered approaches. On the picture in the middle, you see the OECD tiered approach. All tiered approaches divide in stages, the study in stages, trying to exclude exposure in each stage. And if you cannot exclude exposure, you go to the next stage. So the number of stages varies from one approach to another, but in general, you can say that it starts with literature documentation review. If you cannot exclude exposure based on that, you go to straightforward measurements. If you cannot exclude exposure based on that, you go to complete study with a large set of equipment. We've done some research on the measurement devices, and we came to the conclusion that for the basic tier, in clean rooms, it's best to use a CPC. And it is because it can measure really low concentrations, it has no internal background generation, and it provides a time series of particle number concentrations. So the question, can you exclude exposure, yes or no, can be answered by it. But you have to check the size range sensitivity. Of course, it needs to meet your needs for detecting particle sizes. And it's advised to use several portable devices to compensate for spatial variability, for instance, for the near field and far field assessment. For the expert tier, a combination of measurement devices is used. First of all, to measure exposure in different metrics. We're still not certain what would be the best metric, either mass or number counts or surface area concentration, to do the risk assessment in. Besides that, different devices have different size distribution ranges where they measure, so you need several devices to cover the whole relevant size distribution. Also to get insight in concentration in relation to the size distribution. So are the most small particles or most large particles? And besides that, it would be good to take samples to perform offline analysis to identify the particle, so the morphology, the chemical identity, and the agglomeration state. So it is possible to measure. We do have models, and then we digged into the possibility to combine measurements and models. So the first thing that we did is make a comparison between the art estimations with the measured data. And we found out that they are in the same order of magnitude, even though art is not calibrated for nanomaterials. But unfortunately, art estimates in mass, while the measurement data were in particle number counts. So we needed to recalculate the number counts into the mass. So there were many assumptions included in the calculation, so we cannot really draw this conclusion that art is good enough to replace measurement data. Besides that, it was difficult to interpret the measurement data because they were not generated for the purpose. Art also offers a possibility to combine measured data with the model estimation. And what we saw is that that pulls the estimate towards a realistic value and narrows down the confidence interval. And the effect is best for many small data sets per company, including several workers. So the recommendation that it leads to is, since measuring in clean rooms is unpleasant, because devices may bring contaminations into the clean room, and because the devices are rather big, processes may be disturbed, and art appears to be promising in its estimation, it could be a solution to try to improve art for the semiconductor specific conditions. This could be done by adding low concentrations to the calibration data, or we could create data sets that can be used for Bayesian statistic to combine the estimate with the measured data. Anyhow, if we want to create measured data sets, we need to spread it over companies. We need a harmonized measurement protocol, making it easy to compare different data and collect sufficient contextual information to make the link with the model. So to end, the main gaps that we encountered is the availability of quantitative tools. It's very limited, and once you find state-of-the-art tools, it's not per se applicable to semiconductor conditions. The required input data, most importantly related to the nanomaterial itself, are often quite difficult to obtain. The availability of threshold values or toxicity data is a common problem. It's not semiconductor specific. As Fiona told you before, there's also a generated nanomaterials problem where we don't know the composition. So the problems for the purchased nanomaterials is even bigger for the generated nanomaterials. And we noticed that there's no harmonized sector-specific, preferably, measurement protocol available. So I want to thank you for your attention.
Thanks very much indeed, Maaike. That was a very detailed presentation. We now come to a brief moment where we could take some questions from participants, if you would like. So please feel free to unmute yourselves and ask any questions that you would like, or alternately, write them in the chat function of the webinar software here. I'm just going to switch the screen over to Daniela while we do that. So, because as Daniela will be our next presenter. So Daniela, can you hear us?
Yeah.
That's super. I'm just...
Can you see the screen?
Let's have a look.
Yes.
Yeah, that's great. Thanks very much indeed. But before you start, Daniela, I just wanted to check if there are any questions from people from the two presentations that we have so far. Everybody seems very quiet, but I'm sure we can save them up until the end if need be. Okay, no, that's no problem. So, Daniela, do you want to get started? And we look forward to your presentation around competences development and training. Thanks very much.
Thank you. So my name is Daniela Iacopino, and I work as a researcher in the nanotechnology group of the Tyndall National Institute in Cork in Ireland. So I suppose our contribution to the project was related to our competencies on nanomaterials and their properties, and also, as I will show you in the next 10 minutes, on the development of training packages. So the activities of the work package 4, particularly within NanoStream, were associated to the creation of an internal communication family, I suppose, and also of the training, development of training packages. The idea here was to really get the communication going within the partners in order to create a platform for sharing information, and also on the design of safety training packages, especially with emphasis related to nanomaterials and their use on processes relevant for the semiconductor industry. Before we started this activity, we kind of asked ourselves, why do we need additional nano safety training packages? And I suppose the answer that we gave to ourselves was the fact that nanomaterials do have unusual properties, which are very often different than the properties of bulk material, and which are not covered by existing safety training curricula. And moreover, the training of the workforce is also recommended in the CPA guidance for handling of nano objects in the workplace. Again, before we started developing the material, we carried out an internal survey within the NanoStream community to establish again the need for safety training packages. And we found out within this exercise that actually the majority of partners use still generic chemical safety training material, in which the risk associated with a certain material was still evaluated based on the MSDS sheet. And only 3 out of 14 partners had in place training packages tailored to nanomaterials. And no partners had specific training for nanomaterials used in semiconductor processes. So there was definitely the need for development of further training packages. Oops. Can't go ahead. I seem to be able to go forward. Oh yeah. So there are a few processes that we could have taken in consideration, but again, after internal discussion, we decided that CMP was identified as the most relevant process. And Fiona already talked in detail about this process, but just to remind ourselves that CMP is largely used within semiconductor industry, that the process is carried out with slurries, which contain abrasive grains in nano form based on cerium dioxide, silicon dioxide, and aluminum dioxide. And again, there are the exposure scenarios which we identified were mainly 2. So there could be an exposure during normal operation mode, like drum change, pumping, handling of wafers, or during maintenance mode, like accidental skin contact with the content of the chamber, or removal of wafer pieces, and so on. This is then, accordingly, we developed 3 training packages. One was dedicated to operators and maintenance engineers. The other one was for professional EHS, and the other one was actually again dedicated to EHS professionals, but it was mainly train the trainer package. And I'll go through some details of these 3 trainings now. So the first training was for maintenance engineers. And I suppose the aim of the, so it was designed to cater for industry operators which had no previous experience in handling nanomaterials. And the aim of the training package was to increase awareness on general properties of nanomaterials, and then specifically on those materials used in CMP processes. And so the idea of the training package was then to expand from traditional training packages by including information on slurries and CMPs, and also by giving an overview of the risk of the approach developed by NanoStream, and also giving some insight and overview on nanomaterials kind of coming down the line in the near future in ICT applications. This is what this is an overview of the training package. So it comprises about 90 slides, and it is in a kind of PowerPoint format at the moment, and it was taught as it comprises 6 parts, and so it can be delivered as one block, say, of 2.5–3 hours, or individual parts can be taken out and maybe integrated by individual end users into their own safety training. We then carry on with the development of the second training package, which was designed for EHS professionals, with the aim really of increasing knowledge on how to manage kind of risk assessment on nanomaterials. And so the idea here was to show limitation and boundaries on the application of traditional methods, and also to, I suppose, provide methodologies, especially those developed by the NanoStream consortium, which are pragmatic in nature and should allow to conduct environmental assessments in a safe way, even though still in a limited manner. So the training package is again in PowerPoint format, and it comprises 67 slides. And it covers the following topics. So it gives general definition, application, properties, and risks associated to nanomaterials. And then it gives an overview on the legislation and risk assessment with its gaps and limitations. And then it presents the kind of NanoStream risk assessment approach. And then it applies kind of this approach to CMP. The last training package we developed was the so-called Train the Trainer, and the need for this training package was because basically we realized that EHS professionals who will love to deliver our training packages will need themselves some kind of background information on the developed training packages. And so the aim of the Train the Trainer work package was really to create a user format guide to allow the proper delivery of the previous developed training packages. And so this training package is slightly different because it is in a Word format, and basically what it is the narrative, the slide narrative of the 2 previous training packages developed. And so in this way, okay, it provides the narrative, and also it provides some background information, again, on the use of nanomaterials in semiconductor processes, especially in CMP. So these are the 3, this is an overview of the 3 training packages. This material, the development of this material was very welcomed, especially by the industrial partners of NanoStream. Within these tasks, we also try to, as I said, to kind of envisage the use for this material. So again, we conducted kind of a survey within the partners, and we discovered that, again, the development was very appreciated, and partners are planning to use either the whole entire block of the training package, or take parts and maybe integrate them into their own training packages. And also in terms of way of delivering, the partners suggested the way they see this taking life is either as a training-led presentation or maybe as incorporation into e-learning platforms. The consortium also developed as clear plans for the access of this training within the length of the project and also beyond the length of the project, and also the possible access of this material to partners which are outside of the consortium. So this was my last slide. I can give it back to you, Claire.
Thanks very much indeed, Daniela. And in fact, I just stole it back from you. So that was really good. We would certainly be interested in finding more about training and making it more accessible beyond immediate projects. We can ask that at the end of the webinar. So I would like to hand over now to our next presenter, Peter Belde, who is going to talk about another really important aspect of building community trust around nanomaterials, and that is the communication of risk along the supply chain. So Peter, if you want to get started and introduce yourself, that's really great.
Okay, thank you, Claire. Yeah, my name is Peter Belde. I'm a senior EHS engineer for NXP Semiconductors located in the Netherlands. Next slide, please, Claire. And I will talk about how the risks, especially of purchased nanomaterials, are communicated along the supply chain, the regulatory framework around it, but especially the experiences in the NanoStreeM project, especially the first part of the project, where we dealt with this communication from our suppliers to ourselves as downstream users. And I will finally tell something about the recent developments in REACH concerning nanomaterials. Next slide, please. So the regulatory framework when talking about chemical risks in Europe is REACH. And although there is no reference to nanomaterials in REACH, the definition of a substance also covers nanomaterials. And REACH states that the safe use should be independent on form, or should be there for all forms of a substance. And so the risk communication should take the form into consideration. And that means that the supply chain, for the supply chain, there are really no differences in responsibilities regarding normal chemical substances and nanoforms of those substances. Next slide, please. So what were the experiences in the NanoStreeM project when looking at this communication of risks along the supply chain? Well, as I said, especially at the start of NanoStreeM, in work package 1, the first step was to make an inventory of nanomaterials in the semiconductor industry. As you already heard several times, the CMP materials are the most heavily used materials in the semiconductor industry. And if you talk about those materials, in essence, they have really simple ingredients, but of course the production of the nanoparticles in those materials can be quite complicated, and it can be even further complicated by coating those nanoparticles in the production process. And although we didn't research the supply chain, most of the discussions between industrial partners, the conclusion was that the supply chain is relatively simple. You have the raw material, there is the CMP production, and then the downstream end user is the semiconductor industry. Because that's maybe essentially or essential to name is that the materials do not end up in the project. You could already see that in the presentation of Fiona Moclair. It is used to make our products, but it does not end up in our products. And that means that, yeah, there is a relatively short supply chain. We also got some data which we could use from technical descriptions that usually are supplied by the suppliers of those materials, and they contain things like the size of the particles, morphology, but they do not talk about risk. Could you go to the next slide, please, Claire? So for the communication on the risk of these CMP materials, the SDS was the starting point. But if you look at those SDSs, the nano form is not mentioned. It only mentions the bulk material. It only has data about the bulk material. There are no specific data on toxicology, ecotoxicology for the nanoform, and also almost no proxy data that could lead you to saying something more about the difference between risks of the bulk form and the nanoform, like porosity, redox potential, specific surface area, etc. What you see here on this slide is a part of the inventory with the information derived from the SDS and sometimes also the technical description. And you see that on most aspects there is just no information. And even where there is some information, it sometimes is only about the bulk material. So that means that yeah, there is very little specific information about the nanoform of these materials. Reaching out to suppliers also gave little or no extra information, either not available or talking about, for example, the coatings because of trade secrets. Next slide, please. Luckily, there are some recent developments in REACH. Very recently, on December 3rd, a new regulation was accepted by the EU. And in this, there are, it talks about changing the REACH directives to incorporate requirements to identify and characterize the nanoforms of substances that are covered by the registration. And essentially that means that a chemical safety assessment has to be performed on the different nanoforms for which the registration is valid. That means that you have to look as a supplier or as a registrant to adequate sample preparation, what kinds of routes of exposure are specific for nanoforms, characterization of the nanoform, because it's really important, as already stated before, that you know which is the nanoform that you are dealing with when you are investigating the risks of the nanoform. And also get the supporting physical chemical properties that are specific for nanoforms into this assessment, and if necessary also adapt the test methods, because sometimes test methods are just not working for nanoforms and are really directed to the bulk form of a substance. So this really should help the downstream user to get much more information on the specific nanoform they are using from their supplier. The regulation goes into effect on January 1st, 2020, and it's not only for the new registrations, but also the existing registrations have to be adapted to this. So that's, I think, for the industry, a very good development. This was my last slide. Thank you.
Thanks very much indeed, Peter. And it's always very important to keep on top of the regulatory aspects that may influence your use and development of materials. We are going to jump straight to our next presenter, who has fortuitously just left his meeting and joined ours, which I am really delightful to hear. So I'm going to introduce Michael Jank, and he can introduce himself while I go and find his slides. Here we are. So hi, Michael, can you hear us okay?
Yes, can you hear me?
Yeah, very well, thank you. So your slides are up and you can make the presentation.
Okay, thanks for the kind introduction. We cared in a NanoStream project about materials that come into interest beyond the time being. And the question was, okay, we have a vast inventory about the materials already active in semiconductor processing. However, there's a lot of fuss about things like nanowires, nanoparticles that might come interest and might have some beneficial points for application in future CMOS technologies. And the task was to find out which materials will come of interest and how they will be handled and what conclusions we should draw from those materials portfolio and what to care for in future. So please switch to the next slide. The focus was on engineered nanomaterials, meaning nanomaterials that are introduced as in a form of a nanomaterial, maybe it's from some dispersion from some powder or the like. And the focus was on zero-dimensional, meaning things like quantum dots, nanoparticles, one-dimensional materials like nanowires, nanotubes, and 2D materials like the recently heavily discussed materials, graphene, molybdenum, disulfide, all those sheet-type materials that offer new opportunities for transistor channels. The question was which devices have to be taken into account, what are the applications, what are the materials or materials classes, and as explained, how are they handled. Next slide, please. For doing so, we evaluated the ITRS 2015, which was the last edition of the ITRS, that came with sections on emerging materials and emerging devices for the search phrases that are of importance for finding those materials. And afterwards, we turned to the International Electron Devices meetings and evaluated the proceedings from the very beginnings in 1950s until now, respective to these search phrases. We gathered a huge database and did afterwards a classification like can be seen in the example below for the bespoke graphene material. So it starts from dimension 2 and it's a class of atomic monolayer materials named graphene. Applications are manifold, but with a focus on the FET channel. There's hardly only one technique to transfer this material, and this is a mechanical transfer by exfoliation from a graphite crystal or by transferring CVD grown material on a metal sheet and then afterwards removing the metal. Next slide, please. This gives an overview of all the materials found, or the materials classes, and on the other side, on the main applications. And we found that a lot of work is done in group 4 materials. Okay, that's natural because CMOS technology and silicon technology are, let's say, used as one phrase. Yeah? And the the huge success of the semiconductor industry builds on those materials. But also there's a lot of work done on carbon allotrope materials like carbon nanotubes, fullerenes, not so much, but in the last few years mainly on the graphene. There's another huge group on 2D materials that only appears at 10%, but when looking at this, you have to take into account that this is a very new development, and this gathers only appearances during the last few years. There's also been a lot of work done on compound materials, and also compound nanowires come of interest, and then there's some remaining namings of metals and oxides, mainly in the form of nanoparticles. With respect to the application, we see a big stake in the field of field effect transistors. Okay, that's the working horse of the semiconductor industry, and it's clear that this will be the predominant application class. Single electron transistors comes with the same color because it can also be counted to field effect transistors. Then there's a huge appearance of memory devices that apply those nanomaterials with a big focus on nanoparticles that are integrated in flash memories for optimizing the flash electrode. Then there's sensing capabilities of nanomaterials, which have a very huge surface with respect to the volume, and this gives a very good stake for gas sensing, for liquid sensing, and so on. And last but not least, there's some activities in the field of wiring, especially with those carbonaceous materials. So next slide, please. This gives an example just picked out. So you realize the silicon and field effect transistors are the most frequently named things. And this shows how things are introduced into the scientific community. And the next slide then will show how it progresses and how it develops into a state that further can be, let's say, brought into a production environment. So initial studies typically are conducted on bottom-up processed materials like silicon nanowires that have been grown on a specially defined substrate, maybe some metal dots where you use the catalytic effects to grow a nanowire out of it, and those are then collected, can be dispersed, and can be spin coated on the surface. The problem is you always don't have a control over the alignment of these materials. You don't know where those nanowires will end up, and typically you only can then start either to pick single nanowires, maybe by an AFM tip, and move those around and bring them in the environment of some contacts, or you have to deposit the contacts individually per nanowire. So this is a thing that is not very close to a production environment, because when we skip to the next slide, please, in a production environment, you always have a need for very high yield, very high reproducibility, and a very high homogeneity of the materials that are included. So people, or let me say, when the basic principle is proven by using those bottom-up grown materials, people always tend to integrate them in existing technologies. And on this picture on the right side, you see that there are certain techniques where you can produce nanowires at the edges of some polysilicon features by some edge-defined techniques like edge-enhanced oxidation, and people are very skilled in and develop very tricky schemes to carve out nanowires out of existing features that are already available in the silicon technology. And the only problem you have is that the initial quality of these materials is not as good as you have with the bottom-up grown material. But then they go on and develop refinement technologies. And if you just click once on the slide, this shows how it ends up. So people, the technologies get more mature, and in the end, people succeed in placing lots of nanowires close to each other and integrate them with gates to control them. And people also develop techniques that can be integrated into the existing processing schemes. So when you go to the next slide, please. This brings me to the conclusions. The ULSI processing schemes impose very high demands on the integration of new materials and device features in detail, especially reproducibility and yield are the predominant requirements that have to be fulfilled for each production environment. And with the very bad alignment capabilities you have with bottom-up grown materials that are dispersed and spin coated or transferred by any mechanical technique, people always suffer from difficulties and from high defect rates and from bad yield. So people always look for schemes where they can integrate these new materials, which now are not any longer called materials, but it's more features, into common technologies, so that they are not handled as an engineered nanomaterial anymore, but are resulting from the processing scheme. So top-down nanomaterials and device approaches generally, in our view, do not add additional hazards due to their specific nature. So just to bring it together in one phrase, you can have nanomaterials, nano electronics without the need for handling engineered nanomaterials. And so especially from this field of application and device, from the device view, there are no additional hazards that are introduced by the use of nanoelectronics technologies. So thank you for your attention, and I will hand back to Claire.
Thanks very much indeed, Michael, for the last technical presentation of the webinar today. I am now going to go back to Dimiter's slides because he has a short summary slide at the end to sum up really what the project confirmed at the end. Oh, no, I don't want to do that, sorry. Pardon my slight IT incompetence there. There we go. So Dimiter, if we hand back to you and you can summarize what the main learnings were from the project.
Okay, I mean, I'm also not a very technical person in this, not in semiconductor. I'm a safety specialist. Okay, so we can summarize high level the achievements of NanoStream by several statements. The risk assessment is still technically, methodologically limited. Notably, the available models are very generic, as we have seen, or the identified exposure models are not validated for the semiconductor industry. I think this is one of the conclusions that we can make from the project. Now, what we have seen also is that there is a clear safety knowledge gap, notably in the emission and exposure assessments and measurements. Therefore, it is important to get reliable and standardized particle emission data. That is the harmonized protocol that we were talking about in the project. So we still need to develop that in future work. It may be in a different format, and apply to get more measurements to validate recommended tools. And also the toxicity data about nanoforms of nanomaterials are either frequently lacking, as we have seen from the standard data sheets, material data sheets that safety specialists get from suppliers, or are insufficient to determine occupational hazards. I mean, we also looked into different databases like the NanoRec database or the eNanoMapper database, but the nanomaterials that were relevant for the slurries at least were not available there. So that's also a gap that can be given as a statement. Now, finally, I'd like to say that the public part of our research can be read off from the results section of the NanoStream project website, which you can see down here. And let's go to the final slide.
Oop, wrong way.
Okay, good. So what you see here is the consortium meeting, the last consortium meeting in Kroll on the 8th of October. And this is how our team evolved during these 3 years. So now I'd like to ask the industrial participants to give some, well, a short roundtable if time allows, or to have open the webinar for some pertinent questions. It's up to Claire now.
You're handing it back over to me. Thanks very much, Dimiter.
Yes.
Well, we have approximately 4 minutes left until the end of the webinar, so it will be the fastest roundtable in the history of the universe. But if any of the industrial participants would like to comment on their own experiences in the project, that would be really super, while people also think of questions that they would like to ask. So do we have any of the industrial partners that would like to make a comment on how useful the project was for them and what their priorities are going forward? If you're on mute, by the way, you will have to unmute yourself to say anything. Perhaps I can get started with one of my questions. I was very interested in the training materials that you developed, because one of the priorities for NIA is ensuring that what happens in projects is much more widely available than just in the partners of the project. And I know that projects try to make things widely available, but often they don't fall far from the original project. So what plans are there to make the training resources available, Dimiter?
The training resources are developed for the consortium. However, after the project, because that's a common work, we have agreed that they can be distributed under an open license, because these are publicly funded by different consortium partners themselves. We haven't cleared out the specifics, but we will not impede the dissemination of the training results.
So it's something
maybe
that we
Daniela
could disseminate, for example.
Comment something.
So NIA could disseminate
maybe
that
Daniela
to members.
can. In principle, yes. What we don't want to have is substantial changes of the training packages. And of course, we do want to get acknowledged for the results.
I'm sure we can find a way to do that.
Yeah. But maybe Daniela can comment also on this, because she is a work package leader for the training.
Yeah, I mean, just to say, Claire, this was object of many talks during the length of the project. We also thought that maybe putting it out there on a platform such as Excel could be a good way. Maybe Excel could host our training material. So that could be another way of making it available, especially for other semiconductor companies.
No, that's great. So we can certainly follow up and keep our members at least informed of that future training availability. So would anybody else in the room like to comment on either their experience in the project, or one of the participants ask a question to the partners that we have with us today? All comments are welcome. Everybody's super quiet. But that's really fine. I think this has been a very long webinar.
Maybe I can ask a question actually,
Go on then, Dimiter, you
because
ask.
yeah, okay, because actually this part about future nanomaterials came a bit late in the project. So I would like to ask, do you think that this type of materials can fit the work that we've done so far in the other work packages, in the risk assessment work package?
And who are you asking
like
that question to?
Maaike or Lieve.
Maaike,
whoever
Lieve,
is available.
do you want to respond to that question? You're both still on mute.
Yeah, I thought I'd leave it to Lieve.
Okay.
Well, what we discussed our last meeting, our last consortium meeting, is that applying these new nanomaterials probably will not lead to differences in exposure scenarios. So I think if we assess the exposure correctly, it can be used also for the new materials.
Thanks very much. Dimiter, does that help you answer your question?
Oh, yes, absolutely.
Do we have any other further questions from the floor?
Yes. Am I in the room?
Yes,
Can
you are.
Yes,
Yes.
everyone.
Yeah.
Okay.
Hello, yourself.
Hi, Dimiter. Hi, everyone. I have one question, actually. During the speech from, I guess, TNO about the risk assessment, there is no quantitative, how can I say that, the data for the customer exposure. So it's really hard to set up the limit for the customers who expose the nanoparticles. What is the future concern? I mean, is there any plan to set up? Because the nanoparticles should also have the limit in the future, beside of the occupational workers, actually. So this is my point.
I am not sure that I completely understand the question that you have, but the fact that threshold values are not available, we've tried to find the most applicable threshold values, and if you then look at the exposure levels that we estimated or measured, these are so low that it's very unlikely that it will access the threshold values. But that's for workers, and you were talking about customers.
Yes, this is, I mean, this is the main concern, I guess. Everyone has the really concern.
Yeah. But then you have to realize that the nanomaterials are used during the processing, but they are not in the end product. So the product that it's being sold by this industry does not release any nanomaterials.
Even not as a residue, maybe some of them, they are not also including.
I already stated it in my, this is Peter Belde from NXP. I already stated it in my presentation, but there is absolutely no material ending up in the product. If it would, the product wouldn't work. So essentially, the CMP materials, that's mainly what we're talking about. But this is also true for the other materials. They do not end up in the product as nanomaterials. They are only used in certain process steps to get the features in the device that we want to make the device work. And after such a process step, it's absolutely necessary that nothing of that chemical, or in this case the nanoparticles, stay in the product, because they will only make it impossible for the product to work.
Okay, sorry, I missed the point during the presentation, so sorry about it.
No, I think it's a very relevant question, because we've talked about nanomaterials in, for use in the semiconductor industry, and I think many people would assume that they were in the semiconductors themselves. So hopefully that has answered your question well.
Yeah, thank you. Thanks a lot.
So are there any further questions before we wrap this up? No? Well, I can confirm that we have recorded this webinar and you'll be able to access the recording on YouTube, and we will share the link with you. And we will also share a PDF version of all of these slides with you. So thank you very much to all of our speakers for their hard work in preparing for today, and to all of you listeners who came and joined us for the meeting. I hope it was useful for you, and we will follow up with you directly, probably tomorrow morning, after the epic journey of converting the recording into an MP4 format. So thank you very much indeed, and we look forward to future events like this with you. Thanks everybody, bye.
Thank you very much, Claire. Bye.
Thanks.
Thanks, bye.
Goodbye.